Okay, so I'm going to talk about locality-aware collectives, specifically the Bruck Allgather. So just a bit of motivation, collective algorithms such as the MPI Allgather tend to lack scalability just algorithmically. As you increase the process count, the performance, the cost is going to increase. So we want to optimize the performance and the scalability of all collectives, including the Allgather. So this is focused on the Allgather. So the goal is to reduce the most costly communication and exchange that for additional communication that is less costly. So I'm going to go over just a bit about the performance of computers. So if we look at SMP architectures, so this would be the node on the left here. So something where we have a node with multiple sockets or CPUs, they each share cache. So if you're communicating between two processes that are on the same CPU, it can be sent through cache. So the purple line on the bottom would be the cost of communication if it's on socket, two processes on the same CPU. The red line would be communication between CPUs. Try and turn off. So the red line is communication between CPUs. So these are on the same node, but they're not sent through socket, so they're shared through main memory instead of cache. And then the green and blue lines here are if we send between two nodes. So it goes through the network. The green line is if you have less than 4 processes per node. This is on Blue Waters. The blue line is if you have 4 or more processes per node because you hit injection bandwidth. So the line is actually if you have all 16 processes per node, but the blue dots are timings for anything that's more than 4. You hit injection bandwidth, and then it's a little bit slower injecting it into the network. So the main takeaway here is that on these computers, on-socket communication is cheaper than on node, but between sockets, which is all cheaper than between nodes. And then the other thing that we see on these computers is that we have a bunch of processes per node. So on this one, 16. We want to send all of the data between nodes, and we can use any number of processes to do that. So the x-axis here is just the number of bytes we're sending. The orange line is if we use 1 process per node to send all of these bytes. The light blue is if we do 4 processes per node and they each send 1/4 of the bytes. And then the dark blue is if we have 16 processes per node and they each send 1/16 bytes. So the takeaway is we really want to evenly distribute all of the data among all of the available cores. Okay, so that is really important for larger messages that we're going to be talking about, but it is important to see for some of the comparisons. Now, on more recent computers, like the heterogeneous architecture, something like Summit or Sierra, we have a lot more opportunities for passive communication. So we now have GPUs. All of the data starts on the GPUs. That's where the computation is done. And so we now need to communicate between GPUs, which means there are a lot of possible paths for that. Okay. So if we look at a similar plot to the one before and the cost of communication now, this is on Lawson. The dotted line is between GPUs. The solid lines are between CPUs. And so one takeaway, it's a lot cheaper to communicate between CPUs than GPUs, of course. We get performance that's a little bit different. So if you focus on the solid lines here, on socket, so between 2 cores on the same CPU, is the blue line that's still very cheap. The orange line is on node, but between sockets, and the green line is through the network. And when we get to larger messages here, we actually see that it's more than 2 times as expensive to send on node than through the network. So it's actually cheaper to send to another node and then back to your node than to just send on node. So the main thing to take away from this is that on socket is still a lot cheaper, but now on node is not necessarily cheaper. So instead of with previous architectures where we looked at node aware optimizations, we're now calling them locality aware. And in the case of something like Lawson, we're considering on socket to be local and anything that's off socket to be non-local because they are more expensive. But Oh, and so that was with Spectrum MPI. If we look at Mbopich, it does look a lot better. And so this is benchmarks for Mbopich on Lawson. And you can see that now things line up a bit more like you would expect them to. However, on node is still much more expensive for large messages than through the network. So again, we're going to be looking at on socket. That wasn't really a fair comparison though, because data starts on the GPUs. So we don't really care if it's cheaper between CPUs. The two different ways to communicate are either GPU direct. So this would be sending data directly from GPUs to the NIC. And that's the blue line for sending a single message of different sizes. However, we also could copy to the CPU. So this would be copying all the data to the CPU, sending data between the CPUs, and then copying back to the GPU. And that's the orange line. So as long as you have a reasonably sized message, it is cheaper to use GPU direct. However, only if we're sending one message. If we send some number of messages, that no longer holds, because we can copy all of the data to the GPU or to the CPU at once, then do all of the MPI messages between CPUs, and then copy all of the data back to the GPU one time. So if we send something like 10 messages, we get those green lines. The dotted again is that copy to CPU. You can see by the time we're sending 10 messages, it's actually cheaper to copy to the CPU, particularly for smaller messages. And because we're looking at the Bruck algorithm, we care about these small messages. We are just assuming we're copying to the CPU. So this talk is really just focused on inter-CPU communication because we're going to be copying regardless. The one other thing to take note of is it is still cheaper on these systems to use as many processes per node as possible. So there might be 4 GPUs per node. There are still something like 40 CPU cores. And this is the same plot that I showed before, sending a certain message or messages of various sizes between nodes. The blue line is if we only use one process, and then you can see it gets cheaper as we add more processes, each sending a portion of the data. So we do still want to use all of the CPU cores per node, or at least most of them. Okay, so we're going to look at optimizing between CPUs, between nodes, using CPU cores and using most or all of the CPU cores per node. So related research, locality-aware algorithms have been looked at in a bunch of different areas. So neighborhood collectives, aggregating on nodes to reduce internode communication. Similar research was looked at for the all reduce and recursive doubling. I think there's going to be a talk later in the section that's actually on a node-aware algorithm as well. There's also hierarchical collectives. So I'll go into depth a bit about the Allgather hierarchical collectives. But the idea of hierarchical collectives is just that you have something like a master process per node. And so then you don't have a bunch of communication between nodes because you only have one process doing all the communication. There are alternatives there that you could have, say, 2 master processes per node. Similar idea. And then there are a lot of topology-aware collectives, so using the network to actually optimize. So this talk's focused on the Allgather. So a few of the standard implementations for the Allgather are the Bruck algorithm or recursive doubling are typically used for small Allgathers because these minimize the number of messages that are sent. And then the ring Allgather is used for larger Allgathers because that minimizes the size of data that's communicated. So we're going to focus on the Bruck algorithm for this talk. And so we're looking at small Allgathers. So what is the Bruck algorithm? I'm just going to step through an example here. So we have 16 processes. And in this case, we're saying we have 4 local regions. So these could be nodes, but on Lawson, they would be sockets instead. And they each have 4 processes. So let's say that each process starts with a single value, 1 through F. And the first step of the Bruck algorithm is to send one to the left, receive from one process to the right. And so this shows at the bottom the values we're receiving. And this does wrap around. I don't have the arrows that are wrapping around just because things get complicated. Okay, so the next step, receive 2 to the left, or send 2 to the left, receive from 2 to the right. And then 4, and then 8, and so on. So the red arrows in all of this are the communication between regions. So we can say, see, even at the first step, there's communication between regions. But here we're sending, say, 4 from process 4 to process 3. In this step, we send 4 and 5 from process 4 to process 2, and we send 5 and 6 from process 5 to process 3. So the number 5 is actually sent in 2 different messages between these 2 nodes. So not only are we sending 2 messages, we're also sending the value 5 twice. Isn't great. And then this just becomes worse as we move on. So now there are 4 messages between every process between these sets of nodes. So process 8 to process 0, process 9 to process 1, and so on. And we're sending B in every one of those messages. A is in 3 of the messages, C is in 3 of the messages. So we have a lot of duplicate data here. So we want to look at improving this. And there are a few things that have been looked at in the past. So big thing about the Bruck algorithm, algorithmically, it minimizes the number of messages. However, there are multiple messages between non-local regions, between any set, and data is sent multiple times between a set of non-local regions. So this has been looked at in some other algorithms. So hierarchical collectives have been looked at quite a bit. These are just a few of the papers. The idea of the hierarchical Bruck Allgather would be that we're going to first gather to a single process. So we're going to have the first step of the gather, and then the next step of the gather. So processes 0, 4, 8, and 12 here are essentially a master process per node. And they hold everything from that node. And then we just do a standard Bruck algorithm between nodes. So we're sending one node to the left, receiving one node to the right. Then we send and receive 2 away. And at this point, we would hold all of the data on one process per node. So now we have to go back and do a broadcast on process or on node or on region. And then at that point, everything would hold the data. So there are 6 steps now. However, there's no duplicate data or duplicate messages being sent between nodes because there's only one process per node active per region. So that's great. We have extra local messages within a region, but we know those are cheaper. There's only one message sent between any set of non-local regions, and data is only sent once. However, we have a large number of idle processes there. So if we go back to these steps right here, we have 3 idle processes per node. So the majority of our processes are actually idle during this inter-region communication. So another method that I just want to talk about really quick is this has also been optimized to do multi-lane collectives. So there's been recent research on multi-lane collectives, and these are really optimal for larger collectives, but I want to mention them. So same idea, we start with this initial data, but now instead of doing an all gather or gather on node, we're actually going to start with the between regions. We're going to start with the communication between regions instead of within a region. So the first step would be all processes in region 1 send to all processes or a single process in region 0. So you're sending one region away, all processes are active, but now they're actually only sending a single value. So we send 4, 5, 6, and 7, they're all sent once. There's no duplicate data. And then we send to 2 regions away. So process 8 sends 8 and C, process 9 sends 9 and D, 10 sends A and E, and so on. And these send to region 0. So again, there's no duplicate data. So in this case, we do have multiple messages going between a set of regions, but they're all sending a portion of the data. And then you have all of the data within a region. So then you just have to do your on region all gather. And so that would be the first step, and then the second step. So the multi-lane approaches, they do use all processes per region. They still are algorithmically minimal in the number of messages, and the data is only sent once between any set of regions. However, you do have multiple messages between sets of nodes. And we want to minimize the number of messages per node or per region for the Bruck algorithm, because this is for small data sizes and we care about the message count. However, this multi-lane algorithm is really ideal for those larger message counts. So when you might be using something like the ring Allgather. Okay, so what we are looking at is how can we minimize the number of messages between regions? So we're going to first do an all gather within each region. So the first step, we're sending to 1 to the left, receiving 1 from the right, but only within our region. And then the next step, sending and receiving 2 away. Again, only within our region. And then after that, we hold all of the data on every process within a region. So processes 0, 1, 2, and 3 all hold the value 0, 1, 2. We then do have to reorder them just put them back in the correct order. And then we're going to have one step of communication between regions. So I'm just showing where region 3 sends because there's nothing wrapping around here. So the local process, we can say that each process is locally 0, 1, 2, or 3. So the local process 1, the process 13, it's local process 1, it's going to send one node or one region to the left. Local process 2 will send 2 regions to the left. Local process 3 will send 3 regions to the left. And the same, local process 1 receives 1 region to the right. So process 9 is local process 1, it receives 1 region to the right. We can do this step of inter-region communication all at once now. So each process is sending and receiving to a distinct region. So we don't have duplicate messages between regions. And so then after this step, we do have all of the data on each region. We just need to do an Allgather to collect all of that. So the local process 0 did not do any communication. They're going to do the Allgather with the original data. And so this is the data that we have on each process at the top, and we're going to do our local Allgather once again. So then we get to, after this final step of the local Allgather, we have all of the data on the process. We just need to do another rotation of data. So the Locality-Aware Bruck Allgather has extra local messages within a region, similar to the hierarchical collectives. However, only one message is sent between any set of non-local regions. Data is only sent once between any set of non-local regions. And we're using all of the processes per node now, so that each can send to or receive from a unique set of non-local regions. So this is ideal for smaller messages, such as the Bruck Allgather. So we do have some models. So this is just comparing the standard Bruck Allgather, that's the solid lines, to the locality-aware, which are the dotted lines. This is using parameters for Lassen. So we're using sockets for regions instead of nodes. And then the colors are just different numbers of processes per node. So the orange would be if we have 16 processes per node, the dark blues if we have 4. So you can see that the cost is modeled to decrease as we increase the number of processes per node, but all of these should be cheaper than the standard Bruck algorithm. And so we also have measured results. We've compared to the standard Bruck algorithm, so that's the dark blue. The hierarchical approach is the light blue. That multi-lane approach is the dark orange, and then this locality-aware approach is the lighter orange. The solid or the dotted lines here are the systems MPI. So this is on Quartz. Everything, all of these algorithms are implemented on top of MPI, and I implemented all of them just for fair comparisons. So I also wanted to compare against the system MPI. This is looking at a different number of nodes and also some different numbers of processes per node. So we have 4 processes per node on one node and then on 4 nodes, or across 4 nodes. 16 processes per node with one node. Sorry, that's not right. That's 16 nodes. 32 processes per node, there are 16 nodes, and then 4 processes per node with 16 nodes. And so we can see that as we increase the number of processes per node, we tend to see better speed up. And also we get speed up as we're increasing the number of nodes. So this is on Quartz, and then we see the same thing for Lassen. Again, that's 16 nodes. So it's 4 nodes, 16 nodes, 16 nodes, and 32 nodes. So again, the dotted line is the system MPI. Now this is on Lassen, so it's the region as a socket instead of a node. But again, we can see we can greatly decrease over the system MPI, which were built on top of, but also over the standard Bruck algorithms for these other implementations. So that's all I have. Thank you. If there are any